So we left our star 12.233 billion years old in an interesting situation. The core collapse had stopped because the core had become degenerate. The outside of the star was still ballooning out. It was becoming a red giant. And we said that at 12.233 this growth would stop. What is it that stops it? Well, what's happening is we still have hydrogen fusion in a shell, more and more helium being deposited onto this degenerate core. The degenerate core is becoming hotter, and eventually its temperature hits 100 million Kelvin. When the temperature reaches 100 million Kelvin, something qualitatively new happens. At 100 million Kelvin, two alpha particles can overcome their electrostatic repulsion, and we can get fusion of two alpha particles to form beryllium. In fact, once that happens, very rapidly, beryllium fuses with another alpha particle to form carbon-12. So this is called the triple alpha process. This is the fusion of helium that produces predominantly the very stable carbon-12 nucleus. And because the helium in the core was degenerate, this is a very different kind of ignition of fusion than what we've been used to, because as fusion begins, the core starts to heat up. But as it starts to heat up, it does not expand. Remember, degeneracy pressure is temperature independent. The core maintains degenerate density until it gets hot enough that thermal pressure overtakes degeneracy. During this time, fusion, because it doesn't immediately expand, the fusion and the heating associated with it spreads explosively throughout the core. And for a few seconds, this core produces a luminosity of 100,000 solar luminosities. Not for very long, but there's a huge outpouring of energy, very dramatic. Helium flash is what it's called. This doesn't make it to the outside. You don't see the star suddenly flare up. There is too much star between the core and the outside. The stellar envelope happily absorbs this energy. It expands. What really happens is that this extra output of energy from the core expands the hydrogen fusing shell. And so, in fact, the star's luminosity is going to decrease. Momentarily, when the great pulse is coming out, the atmosphere might balloon out, and in fact, some of it might get blown away. We might get a second mass loss. But expanding the hydrogen fusing shell, which is where most of the star's energy is coming from, actually decreases the luminosity, in response to which the response to ignition of helium fusion is that the star, in fact, contracts, and as it contracts, it heats up. So the structure that we're seeing as the star stops growing bigger and cooler when it hits the helium flash, and in fact it starts heating and contracting, so you see the beginning of the next phase of the sun's trajectory. And what happens is that as the envelope contracts and heats, the deep convection zone that was active because of the opacity at the outside of the envelope ceases. That rises up. We get shallow convection. We get convection in the core, where now helium is fusing, producing carbon and oxygen. So we have a helium-burning core surrounded by a shell where hydrogen is fusing, and in fact they're separated by a layer, not depicted here, of inert helium that's been fused out of the hydrogen, but is not yet compacted or heated enough to produce, to be eligible for fusing. So we still have a hydrogen fusing shell surrounding a helium fusing core. This version of the sun, after the envelope has contracted and the star continues to heat at a pretty much constant luminosity, is what's called a horizontal branch star. And notice that the horizontal branch lasts about 100 million years. It's like the main sequence, except for helium burning, and much, much faster. The sun will have contracted to all of 10 solar radii. Its luminosity is down to 41 times its current value. There's the solar system with Mercury long gone, but the sun contracted. Notice that the orbits of the planets have expanded slightly due to the 30% mass loss in the previous expansion. And when we plot it on the HR diagram, this is what we're seeing. At the helium flash, the sun begins to contract and heat up, and this horizontal branch is the analog for helium burners of the main sequence. There's more variation. The star contracts and heats at almost constant luminosity. For the sun, This will last for a few 100 million years. What happens next? Well, you can imagine what's going on. During this phase, helium has been very rapidly fusing in the core. The core is becoming now depleted in helium. We actually have a core that is inert carbon and oxygen. And around that, we will acquire a helium fusing shell surrounded by inert helium, surrounded by a hydrogen fusing shell. We have this onion version of a star. Eventually, the inert CO core can no longer support the outside of the star, and that collapses to degeneracy. We now have a collapsing inner core again. We have helium fusion in the shell accelerated by the collapse. This increases the luminosity of the star. That expands again and cools the envelope. The motion to the left, where the star was heating and contracting, is reversed. The star now starts to move over to the right to lower temperatures and up to higher luminosities. Again, the envelope cools. We get convective envelope, and because of the high temperature dependence of the triple alpha process, we also have convection in the interior of the star. In big stars, these two regions hook up, and we get a second dredge up where carbon and oxygen, the products of helium fusion, are dredged up to the surface of the star, and we can see them in the absorption lines. This is what happens at 12.365, so a million years have gone by. My times are not going to shift. Everything now starts happening so fast that we won't be able to keep track of it. The sun now balloons even larger than it was and even cooler, and the luminosity is even larger. Notice, if you will, that this diagram, aside from omitting the inert helium shell in between the hydrogen fusing shell and the helium fusing shell, is also greatly exaggerating the size of the core. The entire fusing region, including the hydrogen fusing shell, is probably about 0.1% of the size of the star, and so of the radius of the star. So this is a very tiny core on the inside of this hugely bloated envelope, and because it's so hugely bloated, the gas in the outside of the atmosphere is very weakly gravitationally bound, and so again, every time the star gets large, it loses the top level of its atmosphere. There's a lot of mass loss in this early asymptotic giant branch. Here's the picture of the solar system when the sun has gotten this big. And on the HR diagram, what has happened, as we said, is the leftward motion has been reversed. We're now moving to the right, and we're on what is called the asymptotic giant branch because it asymptotes to that old Hayashi track where temperature is controlled by negatively ionized hydrogen. And as the star cools and expands, what's going to happen is that the hydrogen fusing shell, which was temporarily inactive, begins to be active. It deposits more and more helium so that we have this structure now that is a complete onion. I don't know if I can draw it, but imagine somewhere out there is the star's envelope, and inside it is a shell where hydrogen is fusing, and inside that is a shell of inert helium that's not doing anything, and inside that is a shell, that was helium. Inside that is a shell where helium is fusing, and inside all of that is the inert carbon-oxygen core. And what's going on is, because hydrogen is fusing, it is constantly depositing helium into this inert helium shell, and helium is making deposits into the carbon-oxygen. The entire thing, because the number of particles is still decreasing, is crunching down, and the density and temperature of this inert helium rise. And over here on the boundary between fusing helium and inert helium, we have large concentrations of helium, which suddenly become degenerate and hot enough, and so there are flashes in the helium-burning shell, where the helium-burning shell suddenly becomes fusing and produces a large spike in helium luminosity. What does this do? We got the drill by now. The extra spike in helium luminosity expands the hydrogen shell. That decreases the output of hydrogen fusion. Decreasing the output in hydrogen fusion will cause the envelope to contract and to heat. When this happens, eventually the contraction will reheat the hydrogen. Hydrogen fusion rates will go back up. The helium rate will have settled down. the new increased luminosity will cause the atmosphere to balloon back up. And this happens with a period of like 100,000 years. 1, 2, 3, 4, 5 times. And of course, each time the star balloons out, it loses a lot of its mass to this now stellar superwind is what it's called. Its luminosity reaches a maximum of 5,000. Its radius is as large as it's going to get, 213 times the current radius of the sun out to today's Earth orbit. Again, when the atmosphere cools, we get these deep convection in the atmosphere. We get convection in between the shells. And in a star slightly more massive than the sun, say 2 solar masses and above, we find what we call carbon stars, where, as I said, the carbon and other products of fusion are being brought up to the surface and ejected, and we actually see the star ejecting as they get away what coalesces as actual soot. So we see carbon solids in the stellar wind. An example of a asymptotic giant branch star is Mira. Notice gets harder and harder to find stars in these successive stages because these stages last less and less. That is why most stars are on the main sequence, because any star spends most of its time on the main sequence. Mass loss in a carbon star, by the way, can be on the order of 10,000th of a solar mass per year. So in 10,000 years, a star can lose a complete solar mass. Obviously, these are slightly more massive stars, and the thermal pulse, asymptotic giant phase, lasts only about 500,000 years. And so the star does not completely evaporate. This is what the solar system will look like. And what we are seeing in terms of the evolutionary track is this part, the latter part of the asymptotic giant phase. And then we see something really bizarre. We see the star appearing to heat up at constant luminosity. What is going on there? Well, there is no more fusion. Carbon will not fuse in the sun. There's not another phase of fusion that would cause us to move to the left like hydrogen did initially and helium later. What's really going on is that with these successive pulses, the star is losing its envelope, and we are seeing what we call the star is deeper and deeper until eventually what we're looking at is the bare carbon-oxygen degenerate core. And of course, that makes it look like we're seeing things that are hotter and hotter. So the motion here is a little bit sporadic and not regular, but what makes this motion to higher temperature is basically peering deeper and deeper into the star. The last observation about the AGB phase is that during this asymptotic giant phase, we have other sort of processes. There are enough neutrons floating around the core of the star that there are neutron capture processes that allow the star to synthesize elements heavier than carbon or oxygen. So we get things like technetium being formed in stars with only slightly more than solar mass because of this sort of slow process of neutron capture. We'll see what happens at this very end in our last clip about the sun's tortuous history.